Okay, so in this Q&A, we're going to have a look at how to solve linear simultaneous equations when you have either unknown coefficients in there, like k's, for example, instead of just x and y's. But the approach that we're going to look at will also work for if there are just regular old simultaneous equations, right? If you're looking for certain criteria to be met. The main set of solutions that can come up are you can have a unique solution to your set of simultaneous equations, you can have infinite solutions, or you can have no solutions. So in this Q&A, we're going to have a look at all the different cases here. So graphically speaking, the unique solution would just look like this. You have two linear equations and they cross over at a single point. That's it. So the only way that you get a unique solution is if the gradients are different. As long as the gradients of your two linear equations are different, they will cross over at some point. Doesn't matter how different they are, even if they're only slightly different, they will cross over eventually. So if you're trying to solve a set of simultaneous equations to get one solution, one unique solution, then all you're trying to do is make sure that the gradients of your two equations are different. That's it. So to compare gradients more easily, you should rearrange to get y equals mx plus c. The reason why is because in the context of linear, that m coefficient is the gradient of your linear equation. So what you should do is you should take these jumbled up linears, rewrite them in terms of y equals mx plus c first, and then see where are the equations going to be, where the gradient is going to be the same. So what we're going to do is take equation 1, which is this one here, rearrange until we get y equals mx plus c. So that means getting everything but y over to the right hand side and then splitting up the x component to the constant. And when you do that, it's going to look like this, where k over 3 is the gradient and this term here is your y-intercept, the c term. Exact same thing over here in the equation 2. Now from here, because we're trying to find where the gradients are different, we're going to use a do not equal sign on the gradients of each of those terms, right? Like here's the gradient of the first one, here's the gradient of the second one. We want them to not be the same, because if they're not the same, they will intersect at one point. So what we're going to do here is solve for k. So we have our do not equal sign, rearrange, solve, and we're going to find out that we have a unique solution as long as k does not equal -3 or k does not equal -4. That is how you would solve that equation. Infinite solutions are a little bit different. Graphically speaking, it means that both of your equations are the same line. So what you're looking for in more mathematical speak is same gradient and same y-intercept. The reason why I specify that is because we can reuse the same approach that we used earlier for a different style of question. Right? We're looking for infinite solutions now. Same approach, but we're just going to use different results at the end. Here's the same set of equations, just to save some time. From before, we already know that the gradients will be identical if k equals -3 or if k equals -4. That's where they're the same gradient, right? This is where if we wanted them to not be the same, they had to not be that. So the same would mean they have to be k equals -3 or k equals -4. So from here, all we're going to do is figure out which of these k values would make these two equations identical. Now, one way you can go about that is literally just sub it in, right? So if you subbed in k equals -3, you would get a set of equations. If you sub in k equals -4, you'll get a different set of equations. One of those pairs are going to be identical to each other. Alternatively, you could just look at the vertical translations of each of those linears, so the y-intercept components of the linears, which would mean looking at this term here and equating it to this term here. Those are the y-intercepts of both. And if you do exactly that, rearrange, solve the quadratic, you're going to get k equals -6 or k equals -4. Either of those will give you identical y-intercepts. But because we want both identical gradients and identical y-intercepts, you've got to choose the common element between the two. And the only common element is k equals -4. So here's what happens if you were to sub in k equals -4 into both of those equations. Here's the equations. Here's subbing in k equals -4, and then we're just going to do a bit of rearranging. All I'm doing here and here is multiplying that top equation by -1. And you can see they give you the same equation. That can be a quick fact check for yourself, so you can guarantee that your answer is correct. And then finally, we have no solutions, which mathematically just looks like parallel lines. These lines will never touch. That's what makes it no solutions. So for parallel lines, you need your lines to have the same gradient, but different y-intercepts. So again, all you're going to do is rearrange to get y equals mx plus c, do the exact same working out, but this time at the end, you're looking for what would it take to get same gradient, different y-intercepts. So if we use our understanding, or at least the working out from before, we knew that k equals -3 and k equals -4 would give you identical gradients. We need to figure out which of those will give different y-intercepts. So remember, we want the same gradient, which means we want those set of solutions, but we need to choose the one that also gives you a different y-intercept. Well, we know if we take k equals -4, it's going to give us the same y-intercept, so we're just going to choose k equals -3, because that's going to give us different y-intercepts. And once again, if you were to sub in, like for example, subbing in that k equals -3, you could see that happening. Sub in your -3, rearrange, 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 and you can see equation 1 is y equals -x. Equation 2 becomes -x plus 1/4. So they have the same coefficient on their x, but only equation 2 has a different, well, has a y-intercept of 1/4, whereas equation 1 has a y-intercept of 0. That's it. That's pretty much how this all works. So if you're looking for no solutions, infinite solutions, or unique solutions, you do the exact same working out. All you do is check your answers at the end based on what criteria that you need. So it's always rearrange to get y equals mx plus c, and then you compare gradients, you compare y-intercepts, and you see, what do I want? Do I want them to be the same? Do I want them to be different? That's fundamentally it.